Well, welcome to the Halloween edition of the Origins podcast. And that's the moral of this podcast, which is don't be afraid. Today's edition of the Origins podcast, and I'm your host, Lawrence Krauss, is on spooky physics and why you shouldn't be afraid. The universe, of course, is scary, and it's terrifying in many ways. We may be alone in this vast cosmos, and lots of things are out there, and there's more out there than meets the eye. And of course, that's motivated a lot of woo-woo ideas. And I want to talk about some of them in the context of Halloween today. So today's edition is indeed on spooky physics. So let's begin. Let's begin with ghosts. If you've seen a ghost, then you know you haven't seen a ghost. And why is that? Well, physics is a two-way street. If you actually see what you think is a ghost, then that object that you're seeing is either emitting electromagnetic radiation or reflecting it. And that means it interacts electromagnetically. It interacts with light, it produces or absorbs light, and that is incredibly important because once it interacts electromagnetically, it's detectable. As I'll describe, we can detect electromagnetic radiation across the universe. And we could and minute amounts on the other side of the solar system. And so anything that emits radiation should be easily detectable. And of course, as you know, the claims of ghosts are accompanied by images, but nothing particularly special. But more than that, one of the things that characterizes ghosts is a very important property, and what kills that property is that in physics you can't have your cake and eat it too. Ghosts come in and out of walls. They come into the room and they disappear out of the room, and that's fine if they're quite incorporeal and don't interact with matter. Then of course they can float around and slide through walls. But if you can see a ghost, I remind you that it interacts electromagnetically, and that's precisely what stops you from going through a wall. The reason I'm standing on the floor, the reason my hand doesn't go through this desk that the computer and camera are on, is because the electrons in my hands here, the electric charges in my hand get repelled by the electric charges in the desk. This desk is mostly empty space, but the reason my hand doesn't go through it is because electromagnetic fields are the electromagnetic interaction is so strong. So if you could see a ghost, okay, but the ghost shouldn't be able to go through the wall because it interacts electromagnetically. But if it doesn't interact electromagnetically, so it can go through the wall, you shouldn't be able to see it. This, of course, goes way beyond the question of the existence of a soul or the non-existence of a soul. That where would it reside in a human body when someone dies? Nothing changes and their body decays. But I don't want to get into the more general question of a soul. I want to just talk about the physics. Ghosts can't have their cake and eat it too. And even, of course, ghosts can't eat anything because they're incorporeal. But it reminds me of one of my favorite errors in movies called the ghost error. And it comes from a movie called Ghost, which you may remember with Patrick Swayze. And you may remember it's very poignant. He dies and he's a ghost, and he tries to convince his long lost lover that he's there. He tries to save her. Eventually he does save her from something, but he tries to pick up a penny and he can't do it because his hands go through the penny, because he's a ghost after all. But you notice each time he sits on a chair or walks on the floor, he walks on the floor. So somehow his butt or his feet have some incredible properties that he doesn't have. And the reason if he can sit on a chair is because he's interacting electromagnetically. So the ghosts that you can see, are due to something that isn't a ghost, because if you can see it, it can't go through walls. Okay, that's a simple one. Let's talk next about witches. Another important aspect of Halloween One of my favorite historical discussions of science, and there's some evidence for this, and I haven't done it myself, but it seems plausible, is the claim that Newton's laws ended the burning of witches. Ultimately, because the two happen to coincide temporally around the same time. Now, of course, um, coincidence is not causation, and correlation is not causation, and so they could just be an accident that the two things happen. But the argument is made that once Newton was able to show that even the most far-fetched parts of the universe, the motion of the planets around in the solar system, could be governed by physical laws. In fact, everything could be governed by physical laws, and therefore all physical effects have physical causes. The argument was then made, well, then the fact that there's bad weather isn't due to some witch's desire; it's due to some physical cause. And so the notion that witches could, by their desires or their potions or their incantations, affect the universe uh, seemed ridiculous when you knew that in fact the motion of the planets was not serendipitous. It was in fact governed by a simple law of physics, the same laws of physics that governed an apple falling from a tree on Earth. And even though it happened 400 years ago, people still like the idea of witches. The idea that you can cause things to happen by either doing an incantation or creating a potion, that somehow you can affect things remotely. Now, this idea of affecting things remotely without directly interacting with them, without touching them, for example, is characteristic of another real problem and real misuse of physics. Perhaps the biggest misuse of physics I know of today, and it's often in books like The Secret and everything else, and it's due to quantum mechanics. After all, quantum mechanics, speaking of spooky physics, quantum mechanics, Einstein objected to quantum mechanics because it implied, quote, spooky action at a distance, as he described it. And quantum mechanics is spooky, but just spooky enough, and not too spooky. And it doesn't allow the kind of nonsense that is being promulgated. The idea, of course, one of the key ideas of quantum mechanics, which is so strange, is that an observation can change the characteristics of a system. In fact, that a system like an electron, which is potentially orbiting, rotating around and has its angular momentum pointing in any direction, when you actually measure it, it will have it measured pointing in some direction. But before the measurement, it can be pointing in all directions, and that's a property of quantum mechanics. It's weird and spooky. So the observer appears to change the outcome or change the state of the system, or the ultimate outcome is affected by an observer. So that gives the notion that somehow observers have a special place in the universe. And of course, the first idea is that observation has something to do with consciousness. It doesn't. In physics, an observation is when a particle collides with another particle. In some sense, it's doing an observation. There's nothing related to humans, consciousness, or anything like it. Okay? And that's the first misnomer, the first misunderstanding. But the other idea is that somehow, because certain aspects of quantum physics appear classically to suggest action at a distance, that an observer can actually affect things just by looking out at the universe and by thinking about something. So, of course, as The Secret and other things say, if you want good things to happen, you can change the universe. And the argument is that quantum mechanics allows you to do it, that by wanting things to happen, you effectively change the outcome of the universe and good things will happen to you. Or, of course, if you're a witch or doing something evil, that similarly, if you want bad things to happen, that bad things can happen to other people because you want them to happen without doing anything. Nothing of the sort. Not only does observation have nothing to do with consciousness, but this notion that you can affect other physical systems without having any physical contact is not a property of quantum mechanics. In order to produce the kind of weird, spooky action at distance that I'll talk about, having to do with entanglement later, the system has to be very carefully prepared and not only in contact initially, but actually part of the same quantum state. That you have to have a specially prepared quantum state, and different parts of it can be separated and then produce weird, spooky action at a distance. But there's no way that physical systems that aren't interacting, have never interacted, and aren't very specially prepared, and then never get to interact with their environment between the time they're prepared and the time you make a measurement, or the spooky action at a distance happens, then none of this can happen. So this notion that quantum mechanics allows a consciousness to have some special nature in the universe is wrong. And secondly, the fact that quantum mechanics suggests somehow that you can change the way something's going to happen at a far distance without physically directly interacting with it, either touching it or sending some signal, or having a force that affects the motion of the particle, that's complete nonsense. And that's a good thing for us, because it means that nature isn't so crazy. But it's also a bad thing for witches and other people who wish to affect the universe merely by thinking about it. Thinking about things can affect you and the way you think about the universe, and whether you think that something good or bad happened to you is whether it's good or bad. And of course, we're all the rulers and creators of our own demons, so that our the way something affects us is up to us, but the way something affects someone else that's remotely distant away from us is not up to us unless we interact with him directly. Now, as I say, the source of all this, the reason that people somehow think that quantum mechanics allows action at a distance, and Feynman and Einstein called it spooky action at a distance, was what we now call entanglement. And the notion of entanglement, which I've talked about in this podcast a lot, in the context of quantum computing and other things, is a very strange property, which is that if you take a quantum mechanical system, say 2 electrons, and the spin of one electron is pointing up and the spin of the other electron is pointing down, well, not up or down, but you arrange them so their spin is always pointing in opposite directions. So the 2 spins cancel. Now, again, in the quantum system, once you've done that, created that initial state, they can be pointing in all sorts of different directions until you measure it, and then you'll measure it, and let's say if I measure this one, I see it pointing up, I know the other one's pointing down. If I measure this one and see it's pointing that way, it's spin pointing that way, I know the other particle spin is pointing that way, because the net quantum system in this case has a 0 total spin. The 2 things cancel. Okay, great. Then what happens is, if I separate them and I don't allow either one to interact with the outside environment, so that quantum mechanical state hasn't changed, and that quantum mechanical correlation remains between them, then even if I have one here and one in Alpha Centauri, the really strange thing is they're correlated. If you think about them classically, they look like they're separated. Quantum mechanically, they're just part of a single quantum mechanical state. And if I make a measurement of part of that state, in this case on Earth, I make a measurement and I see this particle is pointing up, its spin's pointing up, that other particle spin will be pointing down. Should another observer measure it, it will be pointing down. Instantaneously, that's determined. Now, it seems like some communication is happening faster than light if something is 5 light years away, and I measure this up and instantaneously that one is down. But it's not the case. It seems strange because classically we think of these as 2 separate particles. They're not. They're part of one quantum mechanical state. Moreover, there's no communication that's happening. There's no signal you can send. Because, again, if I measure the electron, a set of electrons that are pointing either up or down, 50% of the time their spin will be pointing up, 50% of the time it'll be pointing down. Now, so let's say I have this state, and it's like this or that, and I measure this particle and its spin is pointing up, and I know that spin is pointing down. An observer will measure that to be pointing down, nothing special. The next electron may be pointing down, this one will be pointing up. And what you'll find is both observers will still measure 50% of the time the particle they measure, the spin will be pointing in one direction on the z-axis and another time the other direction on the z-axis if you're measuring the z component of the spin. Now, there's no way that this experimenter at the other end knows anything's been happening at this end. The only way that anything strange can be determined is if this observer makes the measurement, then makes a phone call and tells this observer, if you measure that electron, its spin will be pointing down. and that the observer can do, and that will be a demonstration that the two particles were entangled. But there's no signal, there's no faster than light signal, there's no communication, and in a sense, in a quantum mechanical sense, there's really no action at a distance, because the quantum mechanical state was created when they were together. And all you're measuring are different characteristics of the quantum mechanical state. Classically, of course, it seems crazy and it seems spooky and it looks like there's action at a distance. But that's just because we're thinking about it classically. We quantum mechanics is so strange because we don't see quantum mechanical correlations in general operating on the scales of human beings and objects we can see in our rooms, and therefore quantum mechanics seems very strange. But this weird spooky action at a distance is only spooky because we're thinking about it classically, because we're classical objects. When you think about it quantum mechanically, it just is what it is. So the bottom line is entanglement doesn't give you an out to create action at a distance, to affect the world somewhere far away that you've never measured it, and to hope that you do an incantation that will cause good or bad somewhere else, or that if you hope that good things will happen to you, then they will happen. And so we come back to Newton 400 years ago. Physical effects have physical causes, and if you want to have a physical effect far away, you better have a physical cause changing that. And so much, therefore, for that kind of witchcraft. Now, another not so spooky, but maybe a related aspect of this kind of thing is miracles. Miracles are usually good things. It's hard to define what a miracle is. A miracle is, you might say, that which is so unlikely that the most probable explanation is supernatural. Namely, the laws of physics, any kind of application of laws of physics cannot explain the phenomena you see, and therefore the most probable explanation is supernatural. That's more probable than what you're seeing is false, or that it's some very rare natural fluke. Now that's the point. How do you know when something is so unlikely that what you're measuring is just a mistake, or rather that it's just a fluke of nature? And that's the hard part, because the universe is big and old, and strange things happen all the time. In fact, anything that can happen that isn't ruled out by the laws of physics is probably happening somewhere in our universe. So the problem is knowing when something is so unlikely that there must be something strange. Now, tied to that is what I could call the X-Files problem of Fox Mulder, who wants to believe. We all are hardwired to want to believe that things that happen to us are significant. They're not just accidents. That special things, when something weird happens to us, it means something. And there's a reason for that. And probably an evolutionary reason. I've talked about it before. The idea that we think intention, there's intentionality in the universe, probably comes from those of our ancestors who survived on the plains of Africa, when they were near the edge of a forest and the trees rustled. You could assume there's nothing there, or you could assume it was a lion. And the people who assumed there was nothing causing the leaves to rustle probably didn't survive long enough to reproduce. So generally, the idea is that you risk less by assuming there might be some dangerous cause to something happening than to assume it's an accident. And so therefore we're kind of hardwired to be on the lookout for strange and dangerous things. And scientists have been subject all the time. Experimenters, if you're doing an experiment long enough, you're going to see something strange, because the laws of statistics will tell you every now and then the result will be strange. If it's distributed, if many possible results can happen, and the most likely prediction is the one that happens most of the time, sometimes the system can give you a strange result, and you got to ask yourself, is that significant or is it an accident? And Richard Feynman, who, as you know, is one of my intellectual heroes and physics heroes, used to actually, in many cases, showed experimenters who made outrageous claims because of what they were making a measurement of, showed that what they were measuring was something much more pedestrian, that they were assuming significance to a fluke accident in their detector. Now, he used to love to, one of the things he used to do, and again, I've talked about this often, is he'd go up to people and say, "You won't believe what happened to me today. You won't believe what happened." And people say, "What?" He'd say, "Absolutely nothing." Because you can have dreams of all of us have dreams that are crazy and ridiculous, But maybe one night you dream your friend breaks their arm, and the next day you get a call from your friend and they've broken their leg, and you say, "Wow, clairvoyance. I saw that in my dream." But you forget the 10 or 20,000 dreams that were nonsense, and it's so and in fact, the likelihood is that if you have enough dreams, one is going to correspond to reality. Uh, Not too surprising that happens, but if it happens to you, it seems very strange, and it's hard to convince anyone that it's really an accident. And the best example I know from that came from Carl Sagan, from his book, A Demon Haunted World, Science as a Candle in the Dark, one of his best books, written shortly before he died. And the example that he gave, which really impacted me when I read it, has to do with the miracle at Lourdes, France, the fountain in Lourdes, France, where, as you know, a vision of Virgin Mary was seen in, I forget what year, in 1800 and something, by someone. And ever since then, people go to bathe in the waters of the river having had that vision of Virgin Mary in the river or above the river. People go there to be cured of various illnesses. And the Roman Catholic Church actually monitors this carefully. And at the time he wrote the book, he said there was something like, they'd recorded something like 120 million pilgrims coming to Lourdes, France, to be cured. And they documented something like 20 some odd cases that couldn't be explained. Cures of cancer. No one regenerated an arm or a leg. But some people spontaneously were cured of things like cancer. And there were some 20 to 25 or something. So that's, if you work it out, that's a probability of slightly less than 1 in a million likelihood that if you go to Lourdes, you're going to be cured. But still, if you're cured, it's a miracle. Well, maybe, but probably not. Because if you look at the random population of people who haven't gone to Lourdes and look at how often cancer is spontaneously goes into remission, how many people experience spontaneous remission of cancer in the population, the number is actually larger than the fraction of those people who went to Lourdes who were cured of cancer. It's better that, I forget the number, but it's more than the slightly less than 1 in a million number for people who went to Lourdes. So in fact, if you go to Lourdes, France, if you just look at the statistics, you're less likely to be cured of cancer. But if you go there and you're a week or a month or a year later or whatever, your cancer goes into spontaneous remission, there's no way on earth I'm ever going to be able to convince you it wasn't a miracle. Because the law of large numbers is hard for us to comprehend. And the notion that things that happen to us are just accidental coincidences, especially when they seem unbelievably strange, is very difficult to fathom. And what we forget is that all day long, for most of our lives, things that happen that aren't unbelievably strange, and law of large numbers and basically and the distribution of events suggests that every now and then really rare, strange things can happen. Physicists have to be aware of it when they're doing experiments. We have to be aware of it when we look at the universe. Strange events are happening in the universe because there are 100 billion galaxies, each containing 100 billion stars. And as I say, anything that can happen will happen. So strange things like black holes, which are rare, appearing in pairs and colliding with each other, which you'd think would be really rare, but they're actually happening fast and often enough in that big universe for the LIGO gravitational wave detector to detect them every few weeks. And of course, they won the Nobel Prize for first detecting them. And same with, let's say, exploding stars. Stars explode very rarely, which is fortunate for us, maybe once per 100 years per galaxy, which is very rare. But there's so many galaxies in the universe that if you look at it, all the galaxies we can see, there's a star exploding every second. And so rare events happen all the time in a big universe. Rare events happen to us rarely, but that's the point. When they happen rarely, it doesn't mean they're significant. And so many things that are attributed as miracles are just viewed as miracles because it's hard to fathom the actual probabilities involved and how unlikely something is. Because remember, to be a miracle, it has to be so unlikely that any natural explanation doesn't work. And the probability that it's false or a natural fluke is much smaller than the probability of it actually being supernatural. And that's all, as I say, that's hard to ever test And I think the onus of proof is on people who declare it supernatural. And in general, as the miracle of Lourdes shows, if you think about it carefully, it isn't. Now, the next thing I want to talk about, well, let me talk about werewolves for a brief second. I was just thinking about werewolves the other day when I was thinking about doing this podcast on for Halloween, and and here's a simple reason why werewolves are. I mean, if you really want a simple reason why werewolves aren't happening, I was just watching, that program Wednesday, which I happen to enjoy, and the werewolves are a key part of it. But the point is, when the moon is at a certain point, a human changes into a werewolf, changes in size, the hair grows, and everything else. Well, that's obviously supernatural. But let's just think about the physics of it. Okay, they get bigger, they gain weight, they gain material, they get mass, they get they get grow hair. So let's take the simplest idea that it's just chemistry, okay? That somehow, due to something, chemical reactions, the same chemical reactions that cause a tree to grow, that take carbon dioxide out of the air and water from the ground, merge it, forming into organic materials that allows a huge tree to grow. It's amazing that it happens, and it happens. But how much energy does it take? Well, I was thinking about this. If you want to gain 1 pound of mass, how much energy do you have to generate to do that? Or let's say lose a pound. That's probably easier. How much, if you want to lose a pound, how much energy do you have to expend to do that? And if you're relatively active, you're expending about 100 watts of energy, maybe 80 watts of energy if you're sleeping, maybe 120 if you're really active. So averaging around 100 watts. To lose a pound, you'd have to expend an additional 100 watts of energy beyond your normal homeostatic energy usage for continuously for 30 hours. Okay? That's to gain 1 pound. Now, if you want, that's so 30 hours to gain of 100-watt expenditure to gain 1 pound. But what if you want to lose a pound, excuse me. What if you want to lose that pound in a minute instead of an hour? Okay. Well, then you got to have 60 minutes per hour and then 30 hours. So you have 1,800 times that. So you need 180,000 watts. Okay. But that's just to gain 1 pound. If you wanted to gain 10 pounds by using chemistry, you'd have to find somewhere 1.8 million watts, 1.8 megawatt generator to do that. So clearly, just to generate additional mass by chemistry, the amount of energy required is ridiculous. But what if you wanted to do even something more miraculous, which is to create mass from nothing, from pure energy? Okay, instead, not use existing materials like carbon dioxide and water, but you just wanted to pop it, pure energy, mental energy or any other kind of energy, and turn it into matter. Well, of course, then because of E equals mc squared, things are even much more ridiculous. You'd need something like 1,000,000 billion times as much energy to produce that mass out of nothing than you would by chemistry. So the laws of physics say, well, if you want to turn into a werewolf, that's fine, but you're going to have to get a power source comparable to the mass of the sun probably to do it. So it's not likely to happen. I think the last thing I want to talk about of spooky things, and it's kind of like action at a distance in a way, is ESP and telepathy. Something that people really want to believe in. I mean, when I look at my dog who's sleeping down below me right now, I feel I can sort of understand what he's thinking. When you look at your child, you feel you have a connection and you know what they're thinking. And of course, if you get to know their behavior, you do have an idea of what they're thinking, but you really feel there's something connecting you beyond just that. That somehow you can read their mind, that somehow there's some signal going between you and them. I hope I've already described how quantum mechanics doesn't allow for that random action at a distance. But even more than that, if you're thinking, then what are thoughts? Well, thoughts are electromagnetic impulses in your brain, right? Neurons firing, and we can measure that we put these helmets on, and we can measure what you're thinking, and that's one of the ways we're trying to figure out how to do implants to allow people to um, to know what they're thinking, so that we can then use external devices to help them move their limbs if they can't control them. And so the key aspect of our thinking is electrochemical, is electromagnetic radiation. So and the point about this is that electromagnetic radiation, which results whenever there are currents and turning on and off, is the easiest thing in the world to detect. And so when we try and detect, so if I'm trying to communicate to you telepathically, I have to have a signal that I send to you. How can I send you the signal? Well, the first thought is, well, I'm producing electromagnetic signals from my thoughts, so maybe those electromagnetic signals are going from my brain to your brain. The problem is, if that were true, we'd easily be able to measure it. I once, when I wrote my book Beyond Star Trek, I estimated, using one of our large telescopes on Earth, we could detect the energy emitted by a 100-watt light bulb on Pluto. And that seemed far-fetched. But it's actually not very far-fetched at all. Because I worked out late, and then I just checked the Deep Horizon spacecraft, which went out to Pluto and is well beyond that and still in communication with us, has a 12-watt transmitter, and we still get the signals from that small device. And so nothing is easier to detect in the world than electromagnetic radiation. So if our brain waves were being received by someone else by electromagnetic radiation, we would have already been able to measure it easily by now, and no such measurements ever been performed. So you may say, well, of course then ESP isn't being, those signals aren't being generated, aren't being promulgated by electromagnetic radiation. They must be promulgated by something that's much harder to detect because we never detected it, But the problem is that, once again, physics is a two-way street. Either it's strong enough to produce a signal in your brain, in which case we could detect it, or it's so weak we can't detect it, and then you got to figure out how it's going to produce a signal in your brain. Say, for example, I was somehow emitting neutrinos. There were nuclear reactions going on in my brain that were emitting neutrinos, because neutrinos are so weakly interacting that they go right through the Earth without knowing it was there. And as I've often talked about, there are 100,000 billion neutrinos going through my head every second from the sun, from nuclear reactions in the sun, and they go right through the Earth without even knowing it. The average solar neutrino can go through a light year of lead at least without interacting. So neutrinos are a great candidate for something that we can't detect easily, although we've managed still to detect neutrinos with large detectors. But the problem is, because they're so weakly interacting, they don't produce any effects. If I produce neutrinos here, they're going to go right through your head without interacting, except for extremely, extremely rarely happen. So neutrinos don't work. Well, what's weaker than neutrinos? Believe it or not, the weakest force in nature is gravity. It's unbelievably weak. I actually did another calculation. I was just reminding myself, and Beyond Star Trek, I said, say I have two electrons, and electrons repel because they have equal charge. So I take just two single electrons, and of course they'll repel, and one electron will fly away from the other. But let's say I want to put a weight on it to hold that electron down. So I want to use gravity to hold the electron down against the repulsion of this other electron. How big a mass would I have to put on top of that electron to hold it down against the repulsion from another electron? The number works out to be 10 billion tons. 10 billion tons of material would be required to hold that electron down, because gravity is 40 orders of magnitude weaker than electromagnetism. And the only reason it doesn't seem weak to us is that every atom in the Earth is attracting us at the same time, and the Earth is a big object, so gravity feels strong. It's hard to stand up, but the gravitational interaction between individual elementary particles is the weakest force in nature. So even while we can, unbelievably, measure the gravitational attraction of small objects, even though it's incredibly weak, we can measure that interaction. And it's a testament to modern science that we can do that relatively accurately. The problem is that the interaction is so small that it can't produce effects. Because remember, if I'm trying to do telepathy, I'm trying to produce a thought in your mind that I had. And that means I have to somehow generate for you a signal that's strong enough to cause a chemical reaction in your brain to have a thought. And so either the conveyor of ESP is strong enough to do that, in which case we could have measured it 100 years ago, or it's so weak we can't do it, in which case with any modern detector, in which case it's too weak to have affected your brain. So there's that catch-22, that cosmic catch-22, that unfortunately, although we'd all love to have ESP, that or force people to think things that we want them to think, if we're a witch, the physics tells us that can't easily happen. It certainly can't happen in a way in which we couldn't have detected it by now. And so supernatural spookiness, as much fun as it is to think about on Halloween, doesn't fly. So I remember one of my favorite SCTV programs used to have that Count Floyd who used to say, it's very scary, very, very scary. Well, it's fun to be scared, I suppose. And the universe is terrifying in its own way. But the really important thing is you don't have to be scared of the spookiness of Halloween, because it's just a fun day. And all of the weird, supposedly supernatural things that we associate with it are fun and games at best, or scary at worst, but not real. And the real universe is actually far more interesting than the spooky Halloween universe. The real universe of our existence has quantum mechanics with the weird and wonderful properties that are allowing us to build quantum computers, and entanglement and strange things, have neutrinos that are going through the universe, have black holes that have properties that are difficult to imagine, have life, and have objects that are actually mostly empty space, that nevertheless hold together by electromagnetism, and you can lift up because of the properties of electromagnetism. And so even though my table and this cup are mostly empty space, they allow us to have these wonderful lives, and the same electromagnetism allows me to record this podcast that maybe bursts some bubbles. And and bursting bubbles isn't necessarily fun, but as I say, what I've always felt is that the real universe is far more interesting than the universe of the supernatural universe or the universe of science fiction. I said that when I wrote The Physics of Star Trek, and that motivates continuing to study the universe. It doesn't mean there's things we don't understand. There's lots we don't understand about the universe. But what you have to remember is there's lots we do understand, lots of things that have been supported by experiment. And if a claim is made that violates the results of our experiments, like ESP, or performing action at a distance, or anything like that, or having corporeal objects go through walls that are macroscopic, then once it violates known physics, then we know it's not true. So enjoy your candy, enjoy the fun, enjoy the movies, but don't take it too seriously. And with that, I hope you have a wonderful Halloween, and I look forward to seeing you again. Once again, this has been the Origins Podcast. I'm your host, Lawrence Krauss, and I hope you enjoy watching this. If you watch this on our YouTube channel, that's great. I hope you'll subscribe, and you can also listen to it on any podcast site. So have a great day and a great night, and enjoy. Hi, it's Lawrence again. As the Origins Podcast continues to reach millions of people around the world, I just wanted to say thank you. It's because of your support, whether you listen or watch, that we're able to help enrich the perspective of listeners by providing access to the people and ideas that are changing our understanding of ourselves and our world, and driving the future of our society in the 21st century. If you enjoyed today's conversation, please consider leaving a review on Apple Podcasts or Spotify. You can also leave us private feedback on our website if you'd like to see any parts of the podcast improved. Finally, if you'd like to access ad-free and bonus content, become a paid subscriber at originsproject.org. This podcast is produced by the Origins Project Foundation as a non-profit effort committed to enhancing public literacy and engagement with the world by connecting science and culture. You can learn more about our events, our travel excursions, and ways to get involved at originsproject.org. Thank you.